Hello friends, welcome back to my YouTube channel. Today in this 11th part of my discussion on liquid extraction, I will be discussing a numerical. The numerical is based on cross current liquid extraction, multi-stage cross current liquid extraction. The theoretical aspects of this operation I had discussed in part number 10. I'm giving link to the playlist which contains all my videos on liquid extraction. So in part number 10, I had discussed the theoretical aspects of multi-stage cross-current liquid extraction. And today, I will discuss one numerical that is based on multi-stage cross-current liquid extraction. So let us begin the discussion. To begin with, we will look at the numerical statement. If 100 kg of a solution of acetic acid and water containing 30% acid is to be extracted 3 times with isopropyl ether as solvent, if 40 kg of solvent is used in each stage, determine the quantities and compositions of various streams. How much solvent will be required if the same final raffinate composition was to be obtained in a single stage? Here, acetic acid is C, that is the solute to be recovered. Water is A, the carrier solvent, and isopropyl ether is the extracting solvent. So in this case, we have a feed solution, 100 kg of feed solution. The solution is of acetic acid and water, and the task is to recover acetic acid from its solution with water. Initially, the feed solution is containing 30% of acid in it, and it is to be extracted 3 times with isopropyl ether as solvent. When we say 3 times, that means the solution has to be extracted, or the operation is to be carried out in a cross current manner or in a cross current cascade. So this is a 3-stage cross current liquid operation, and isopropyl ether is the solvent that is used, and they are saying that 40 kg of solvent is used in each stage. So with this, we are supposed to find out the quantities and compositions of various streams, that is quantities and compositions of raffinate and extract phases that come out of each stage. Then the second part in this numerical is, they say if the operation is carried out in single stage with the same final raffinate composition, that is the raffinate composition that is obtained after 3rd stage in the 3-stage cross current operation, if the same raffinate composition is to be obtained in a single stage operation, then what is the requirement of the solvent, or what is the amount of solvent that is required for such an operation? That is the second part of the question in this numerical. And the ternary system involved is acetic acid, the solute, we denote that by C. Then we have water, we denote that by A. Water in this case is the carrier solvent, and then the extracting solvent is isopropyl ether, we denote that by B. So this is the numerical statement. Let us solve it. They have also provided us the equilibrium data. The equilibrium data is given in the following table. So this is the equilibrium data. You have data for water layer, water rich layer, and isopropyl ether rich layer. And in each layer, they have given a weight percentage of each of the component. Weight percentage of A, weight percentage of B, weight percentage of C in the water layer, and you also have composition in the isopropyl ether layer. I had used the same numerical in my previous discussions. So while solving for single stage operation, I have used the same data. And now we will understand what will happen if the operation is carried out in multi-stage, 3-stage cross current manner. So this the equilibrium data is also given to us, and we have to use it for solving the numerical. So as usual, first of all, let us note what is given to us. The feed solution in this case is a solution of acetic acid and water. The quantity of feed is given to us. F is 100 kg. Then weight fraction of solute in it is given. We denote that by XF. So XF is 0.3. Then the operation to be used is 3-stage cross current liquid extraction. The solvent to be used is pure isopropyl ether. In each of the 3 stages, pure isopropyl ether is to be used as the solvent, which means Ys is 0. That is weight fraction of C, weight fraction of solute in it is 0. Nys is 1. That is weight fraction of B is 1 because it is pure solvent. Nys gives us weight fraction of B. Nys is weight fraction of B in the solvent phase. And since this is pure B, its weight fraction is 1. And since pure isopropyl ether is used, there will be no any solute in it. And that's why Ys, which is weight fraction of solute in the solvent phase, it is 0. Then the solvent that is to be used in each stage that is given to us. So S10, it stands for solvent used in stage 1, it is 40 kg. Then S20, it stands for solvent used in the second stage, it is 40 kg. And S30, the solvent used in the third stage, it is again 40 kg. So in each stage, 40 kg of solvent is used. The equilibrium data is given to us. So this is composition in weight percentage of raffinate and extract phases when they are in equilibrium with each other. That is composition of the raffinate phase in weight percentages and composition of the extract phase in weight percentages. That is given to us when the raffinate and extract phases are in equilibrium with each other. That's why this is the equilibrium data that is given to us. In this case, the raffinate phase is the water layer or water rich layer, and extract phase is the isopropyl ether layer or isopropyl ether rich layer. Then what are we supposed to find? We are supposed to find quantities of raffinate and extract phases from each stage. That is, we are supposed to find out R1, R2, R3 and E1, E2, E3 in kg. Along with this, we are also supposed to find out the compositions. That is, we are supposed to find out X1, X2, X3 and then Y1, Y2, Y3. So quantities of raffinate and extract phases and compositions of those raffinate and extract phases we have to find out. In the second part, we are supposed to find out the solvent that is required. Let me first erase it. We have to find the composition, let me tell you. In the second part, we are supposed to find out the solvent required. Solvent required for obtaining the same final raffinate composition in single stage operation. That means when the operation is carried out in multi-stage, 3-stage cross current operation, you get raffinate phases with these compositions and then you get extract phases with these compositions. We are going to report those compositions. And they say that if the same final raffinate composition is to be obtained in single stage, that is, if X3 is to be obtained in a single stage operation, then what is the amount of solvent that is required in the operation that we are supposed to find out in the second part. So there are two parts. In the first part, we will find out the quantities of raffinate and extract phases out of all the stages. and then we will also find out the compositions of those raffinate and extract phases. And in the second part, we will find out the amount of solvent that is required if the operation is carried out in a single stage to obtain the same final raffinate composition as was obtained or as is obtained in the 3-stage cross current operation. Okay, so I hope this is clear to you. If you have any doubt, you can mention that in the comment section. Let us move ahead. Now let us start the solution. First of all, we will represent the operation. So this is stage number 1, 3-stage cross current operation. Stage number 1, feed is admitted to this stage. The amount of feed is 100 kg and weight fraction of solute in it is 0.3. It is contacted with fresh solvent 40 kg, S10 is 40 kg, and it is pure, that is Ys is equal to 0. So you are going to get the extract phase, and E1 will be the amount of extract phase and Y1 will be the weight fraction of solute in it. And then we will be getting the raffinate phase. R1 will be the amount of raffinate phase that is obtained from stage number 1, and X1 is the weight fraction of solute in it. Now this raffinate phase is sent to stage number 2, where it is contacted with fresh solvent S20, which is again 40 kg, and it is pure solvent, that is Ys is equal to 0. So it will give out the extract phase whose amount is E2 and weight fraction of solute in it is Y2, and we will be getting the raffinate phase. R2 will be the amount of that raffinate phase and X2 will be the weight fraction of solute C in it. And then this raffinate phase is contacted with fresh solvent in stage number 3. So amount of solvent admitted in stage number 3, it is again 40 kg. It is pure solvent, therefore Ys is equal to 0, and it gives out the extract phase. E3 is the amount of extract phase, Y3 is the weight fraction of solute in it, and you are going to get the final raffinate out of stage number 3. R3 will be the amount of that raffinate and X3 will be the weight fraction of solute in it. So that is the operation, and we are getting E1 plus E2 plus E3. You will get the cumulative quantity of extract phase. E1 plus E2 plus E3. Let us denote it as E, and you are going to get it in kg. Okay, so we are supposed to report E1, E2, E3 and then E. Then Y1, Y2, Y3. Then we are also supposed to report the quantities of raffinate phase R1, R2, R3, and then the compositions of those raffinate phases X1, X2, X3. So this is the operation. First of all, we will plot the graph, and let me tell you, we will need the distribution diagram as well as the ternary diagram. And the ternary diagram, I'll be using a rectangular plot to plot the binodal solubility curve. So on y-axis we will be plotting x and y, that is weight fraction of solute in raffinate and extract phases, and on x-axis we will be plotting nx and ny, that is weight fraction of B in extract and raffinate phases. And then you'll be getting the curve, binodal solubility curve. And then I will be connecting the corresponding equilibrium concentrations in raffinate and extract phases with these tilines. So the composition in raffinate phase, this is connected to the composition in extract phase, this. So this composition in extract phase is in equilibrium with this composition in raffinate phase. Likewise, I have drawn all the tie lines that are given to us. you please remember, tie lines connect concentrations in raffinate and extract phases that are in equilibrium with each other. So we will need this ternary equilibrium diagram. We have plotted it on rectangular coordinates, and then we will also need the distribution diagram where we are plotting x against y. That is weight fraction in raffinate phase, it is plotted on the x-axis, and weight fraction in the extract phase, it is plotted on the y-axis. So for the given data, the distribution diagram is like this. So in our solution, we will be using both the diagrams. This distribution diagram is required to plot the concerned tie line. You'll come to know shortly. The point is, you will need both the diagrams for solving this numerical. So first is we have to locate point F on the ternary equilibrium diagram. So I'll just show the ternary equilibrium diagram. We have already plotted it, and let us now learn how to locate point F. So point F is located with this coordinates 0, xf. So that is, it will be located on the y-axis, and y coordinate for its location is xf. Xf is given to us, it is 0.3. So point F will be located at 0.3. So 0.3 is over here. So point F will be located in this way, and then we will locate S. S will be located with this coordinates nys, ys. Nys is 1 because you are using pure solvent, and ys is 0. So 1 0. Point S will be located at 1 0. So 1 0, it is over here. So this will be point S. So after locating point F and point S, next task is we will connect these 2 points. Connect F and S with a straight line. So in this way, you get this line Fs. Okay, so I hope these are simple steps to locate F and to locate S, and then you have to connect those points F and S to get this line. Now let us move on. Now let us start with calculations for stage number 1. So for stage number 1, again we will be using the ternary equilibrium diagram. We have plotted all this till now. Now let us calculate M1. M1 will be calculated by material balance. I have discussed these material balances in my previous video, where I have discussed theoretical aspects of 3-stage cross-current operation. So M1 is obtained by adding F and solvent. So M1 will be F plus S10. So F in this case is 100 kg, S10 amount of solvent used in first stage is 40 kg. So M1 will be equal to 100 plus 40. That gives us M1 as 140 kg. Sorry. Okay. After finding out M1, we have to locate point XM1. We have to locate point M1, and for that we need to calculate XM1. XM1 is calculated by using this formula. Again, I have discussed it in my previous video. Link is available. You please go and watch it if you have not yet seen that video. So XM1 is equal to Fxf plus S10 into Ys divided by M1. F is 100 kg, Xf is 0.3, S10 is 40 kg, Ys is 0, M1 we obtained previously, it is 140 kg. So therefore XM1 will be equal to 100 into 0.3 plus 40 into 0 divided by 140. That gives us XM1 as 0.21. Now we are going to use this value of XM1 to locate point M. So let us do that. So now let us know how to locate point M1. M1 will be located on the line Fs at x is equal to xm1. So it will be located at nm1 at a point with coordinates nm1, xm1. No, we just can we just have to use the value of xm1. We calculated it previously. It is 0.21. So you just locate 0.21 on the y-axis and then go to the line fs. The point of intersection with the line fs will be nothing but point m1. So in this way, you have to locate point m1. Now the next important task is we have to draw a tile line through m1, because the mixture m1 is representing the mixture that is formed in stage number 1, and that mixture will ultimately settle into raffinate and extract phases. Those will be in equilibrium with each other. That's why point m1 should also lie on a tile line. And the most critical task is to draw a tile line that passes through m1. Let me tell you, we have to do this by trial and error. Okay, so I'll tell you how to do that. A tile line through m1 is drawn. First, you just look at a tile line through m1 that is parallel to the closest given tile line. There is no need of drawing it. You just look at a tile line that will pass through m1 and that is parallel to the closest given tile line. So for example, I will try to find out a tile line that is parallel to the closest tile line in this case is this tile line. So I will be drawing a tile line that passes through m1 and it is parallel to the closest given tile line. And once I have that tile line, then I will adjust the position of that tile line which I had drawn. I will adjust the position so that its endpoints represent concentrations that are in equilibrium with each other. So when you draw a tile line through m1 that is parallel to the closest given tile line, now what you have to do, you have to adjust its position so that the endpoints of the tile line will represent concentrations that are in equilibrium with each other. Are you understanding it? You have to draw a tile line through m1 that is parallel to the closest given tile line. Then you have to adjust the tile line that you have drawn so that the endpoints of the tile line, they will represent concentrations that are in equilibrium with each other. And for this, in order to decide this, you will need the distribution diagram. So you are going to adjust the position of the tile line in order that the endpoints represent concentrations that are in equilibrium with each other. We need the distribution diagram. I have shown. So this is the distribution diagram. So after drawing a tile line through m1, which is parallel to the closest given tile line, now I am adjusting it so that the endpoints of the tile line will be in equilibrium. The endpoints, concentrations represented by the endpoints of the tile line will be in equilibrium with each other. So when I do that, when I adjust the position of the tile line through m1, I get these concentrations. X1, that is the raffinate composition, is 0.255 and the extract composition is 0.115. So a tile line with these endpoints will be a tile line that passes through m1 and which is my required tile line. Initially this tile line was parallel to, I had drawn it parallel to the given tile line, parallel to the given closest given tile line, and then I have adjusted its position, because if I draw a tile line through m1 that is parallel to the closest given tile line, you can check it. The endpoints of that tile line may not represent equilibrium concentrations. You can check it with the help of this distribution diagram. That is why after drawing the tile line, you have to adjust its position so that the endpoints will be representing equilibrium concentrations. So in my case, after I draw the tile line and after I adjust its positions, I get this equilibrium concentrations. So with this concentrations, I will draw a tie line. This black color tie line will be the tie line that I need. Initially, I had drawn it parallel to the closest given tie line. Thereafterwards, I have adjusted its position so that this end point, this will be x1 and this will be y1. This end point will represent x1 and this end point will represent y1. So now I have got that tie line whose end points are equilibrium concentrations, and I have checked that by using the distribution diagram. So this black color line is the tie line that I need in my calculations, that is passing through M1, and the endpoints of which are representing the concentrations that are in equilibrium with each other. Now I will name the points as R1 and E1. The y coordinate of R1 is x1 and y coordinate of point E1 is y1. So all I need in my next calculations is values of x1 and y1. So in order to get them, I have plotted the tie line that is passing through M1. Why there will be a tie line that passes through M1? Because M1 is representing a mixture which will settle into raffinate and extract phases, and after some time those raffinate and extract phases, they will come to equilibrium with each other. So I hope you now know how to draw the tie line. It has to be done by trial and error. You can start with by drawing a tie line that is parallel to the closest given tie line, and then you have to adjust the position of the tie line so that its endpoints will represent concentrations that are in equilibrium with each other, and that you can do with the help of, you can check that with the help of this distribution diagram. I sincerely hope you have understood how to draw the tie line. If you have any doubts, you please mention them in the comment section. Okay, so now I can do the rest of the calculations for stage number 1, because now x1 and y1 they are known to me. So steady state total material balance for this stage will be F plus S10 is equal to M1, that is E1 plus R1. I can write it like R1 plus E1 is equal to M1, but M1 is 140 kg. We have obtained it previously. So that is R1 plus E1 is equal to 140. I am calling it as equation number 1. Then I will write steady state material balance for solute C. So it will be F into XF plus S10 into YS, that is equal to XM1 into M1, that is equal to E1 into Y1 plus R1 into X1. That is, I can write E1 into Y1 plus R1 into X1, that is equal to M1 into XM1. That is here XM1 is 0.21. I had obtained it previously. X1 is 0.255. Again, we just got that value. Y1 is 0.115. We got it. So after using the values, I get this equation E1 into 0.115 plus R1 into 0.255, that is equal to 140 into 0.21. That is, I will write 0.115 E1 plus 0.255 R1, and 140 into 0.21 is 29.4, and I am calling this as equation number 2. Okay, so we have got equation 1 and 2. Equation 1 is R1 plus E1 is equal to 140, and equation 2 is 0.115 E1 plus 0.255 R1, that is equal to 29.4. Now all we have to do is solve these two equations simultaneously, because there are two unknowns, E1 and R1, and then you have to get those two unknowns. So from equation 1, E1 is 140 minus R1, and then I am going to use it in equation 2. So it will be 0.115 into, in place of E1, it is 140 minus R1 plus 0.255 R1, that is equal to 29.4. Then after simplifying it, 0.115 into 140 is 16.1 minus 0.115 R1, plus 0.255 R1, that is equal to 29.4. That is minus 0.115 R1 plus 0.255 R1, that is equal to 29.4 minus 16.1, sorry. So that is 0.14 R1, that is equal to 13.3. That is R1 is equal to 13.3 divided by 0.14. That gives me R1 as 95 kg. And since E1 is equal to 140 minus R1, E1 will be 140 minus 95 and E1 comes out to be 45 kg. So the quantity of raffinate phase coming out of stage number 1 is 95 kg, R1 is 95 kg and E1 is 45 kg. So that ends my calculations for stage number 1. So at the end of calculations for stage number 1, I have got value for x1, that is 0.255. Then I have got value for y1, that is 0.115. Then I have got value for E1, it is 45 kg. And then I have got value for R1, it is 95 kg. Now we have to proceed for our calculations for stage number 2. Okay, so now let us do calculations for stage number 2. So again, we will take our graph. So far we have drawn this graph. Now for stage number 2, the first thing that we will do is we will connect R1 and S. This is to show that we are contacting the raffinate phase that comes out of stage number 1 with the fresh solvent. So we will connect R1 with S. Then we have to calculate M2. And for that we are going to use the material balance. The material balance for stage 2 is M2 is equal to R1 plus S20. R1 we just calculated, it is 95 kg. S20, the amount of solvent used in the second stage is again 40 kg. So M2 will be equal to 95 plus 40. That comes out to be 135 kg. That is M2 is equal to 135 kg. Next, we have to find out XM2. And XM2 will be found out by using this formula. I have discussed it in my previous video, how you get this formula. So XM2 is equal to R1X1 plus S20 into YS divided by M2. R1 is 95 kg and then X1 is 0.255, S20 is 40 kg, YS is 0 and M2 is 135 kg. So if you use these values, you get XM2 as 195 into 0.255 plus 40 into 0 divided by 135. That gives XM2 as 0.18. Then after getting XM2, you have to locate M2. M2 will be located on the line R1S, because after the raffinate is mixed with the solvent, it will form the mixture and that mixture will be represented by the point M2. So M2 will be located as at NM2 XM2, but we will use XM2. We have just got it. So it will be located at NM2 0.18. So let us locate it. 0.18 is over here. And then we will go to the line R1S. And the intersection point will be nothing but the point M2. Then again we will have to draw a tie line through M2. Again we have to do it by trial and error. And we will do the same thing as was done for stage number 1 of the tie line through M1. So a tie line through M2 that is parallel to the closest given tie line. Closest given tie line is first drawn. Then this tie line, the position of this tie line is adjusted so that its end point represents concentrations that are in equilibrium with each other. And for that, you can use we have to use the distribution diagram. So I will draw a tie line through point M2 that is parallel to the closest given tie line, and then I will adjust its position so that the endpoints of the tie line represent the concentrations that are in equilibrium with each other. So if I do that, then I will get these concentrations. X2 is equal to 0.225 will be in equilibrium with Y2, which is 0.095. So these are the concentrations represented by the tie line that is drawn through M2 and which is my required tie line. So I will draw the tie line. This black color tie line will be the tie line that I need. Then the endpoints I am going to denote it by R2 and E2. The y coordinate of R2 is X2, 0.225, and y coordinate of point E2 is 0.095. I'll be using these values for doing remaining calculations for stage number 2. Okay, so stage number 2, where raffinate from the first stage is contacted with the fresh solvent to get raffinate from stage number 2 and extract from stage number 2. Then we can now write the steady state total material balance. It will be R1 plus S20, that is equal to M2, that is equal to E2 plus R2. That is, I can write it like R2 plus E2 is equal to M2, but M2 is 135 kg we have obtained. So R2 plus E2 will be equal to 135. I am calling it as equation number 3. And then we will write steady state material balance for C, that is for solute. It will be R1 X1 plus S20 into Is, that is equal to XM2 into M2, that is equal to E2 into Y2 plus R2 into X2. Then I will write it like E2 into Y2 plus R2 into X2, that is equal to M2 into XM2. That is XM2 is equal, in this we know XM2 is 0.12, we just have found that quantity. Then X2 is 0.225 and Y2 is 0.095. So if I use these values in this equation, it will be E2 into 0.095 plus R2 into 0.225, that is equal to 135 into 0.18, that is 0.095 into E2 plus 0.225 R2, that is equal to 24.3. 135 into 0.8 is 24.3, and I am calling it as equation number 4. Okay, so let us continue. We have got equation R2 plus E2 is equal to 135. Let this be equation, this is equation 3. And then we got equation number 4, 0.095 E2 plus 0.225 R2, that is equal to 24.3. This is equation number 4. Now we are going to solve these two equations simultaneously. From equation number 3, E2 is 135 minus R2, and I'm going to use it in equation number 4. So if I use it, it will be 0.095 into 135 minus R2 plus 0.225 into R2, that is equal to 25.3. That is 12.83 minus 0.095 R2 plus 0.225 R2 is equal to 24.3. That is 0.095 R2 plus 0.225 R2, that is equal to 24.3 minus 12.83. That is 0.13 R2, that is equal to 11.47. That is R2 is equal to 11.47 divided by 0.13. That gives me R2 as 88.23 kg. And now you can get E2 as 135 minus R2. That is E2 is equal to 135 minus 88.23. That gives me E2 as 46.77 kg. Therefore, for stage number 2, we get R2 is equal to 88.23 kg and E2 as 46.77 kg. So this ends our calculation for stage number 2. For stage number 2, we have got X2 to be 0.225. Then we have what Y2 to be 0.095. Then we got even as 46.77 kg, and then E2 has 46.77 kg, and then R2 we bought it as 88.23 kg. Okay, now let us go for calculations for stage number 3. So again, we have this graph that was obtained at the end of stage number 2. Now the first thing that we will do in this case is we will connect R2 with S. This is to show that raffinate out of stage number 2 is contacted with fresh solvent. So R2 is connected with S. Then we are going to calculate M3. M3 will be calculated as M3 is equal to R2 plus S30. R2 we obtain is 88.23 kg. S30, the solvent, amount of solvent used in third stage, it is 40 kg. So therefore M3 will be equal to 88.23 plus 40, which gives us M3 as 128.23 kg. Then after getting M3, okay, now let us go for calculations for stage number 3. So again, we have this graph that was obtained at the end of stage number 2. Now the first thing that we will do in this case is we will connect R2 with S. This is to show that raffinate out of stage number 2 is contacted with fresh solvent. So R2 is connected with S. Then we are going to calculate M3. M3 will be calculated as M3 is equal to R2 plus S30. R2 we obtain is 88.23 kg. S30, the solvent, amount of solvent used in third stage, it is 40 kg. So therefore M3 will be equal to 88.23 plus 40, which gives us M3 as 128.23 kg. Then after getting M3, so location of M3, which is representing the mixture that is obtained when R2 raffinate from second stage is mixed with fresh solvent. So it will be located at NM3XM3, that is NM3XM3 0.15. We are going to use that. So 0.15 is over here. Then we will go to the line R2S. The intersection point will be nothing but M3. So in this way M3 is located. And then again we will have to draw a tie line through M3. Again we will use our trick. First, I will draw a tie line through M3 that is parallel to the closest given tie line, and then I will adjust this tie line. I will adjust the position of the tie line so that its end points represent concentrations that are in equilibrium with each other. And for that, I need to use the distribution diagram. So after drawing the tie line that is parallel to the closest tie line, I will have to adjust the position of my tie line so that its end point represent the concentrations that are in equilibrium with each other. And for that, I am going to use the distribution. So when I use the distribution diagram, after adjustment, I get this concentrations. X3, that is end point of the tie line, which is required. One end point is 0.198 and the other end point is 0.079. That is X3 is 0.198 and Y3 is 0.079. So this will be the end points of the tie line that I need. So I'll draw a tie line and whose end points will be, I'll represent them by R3, E3. The Y coordinate of E3 is 0.079. You can check. And then the Y coordinate of R3 is 0.198. You can check that. So in that way, I have drawn the third tie line which is required, and I have got these values. Then I am going to use these values to do the remaining calculations for stage number 3. So stage number 3, in stage number 3, raffinate from stage number 2 is contacted with fresh solvent to get extract from it and raffinate from it. So when you write the steady state total material balance for this stage, it will be R2 plus S30 is equal to M3, that is equal to E3 plus R3. That is R3 plus E3 is equal to M3. M3 is 128.23 kg. We obtained it previously. That is R3 plus E3 is equal to 128.23. I'm calling it as equation number 5. And then I'll be writing steady state material balance for solute C. It will be R2X2 plus S30 into Ys. That is equal to XM3 into M3. That is equal to E3Y3 plus R3X3. Then E3Y, I can write in this way, E3Y3 plus R3X3, that is equal to M3XM3. XM3 is 0.15. We obtained it earlier. X2 is 0.198. Y2 is 0.079. So when I use this, I will get E3 into 0.079 plus R3 into 0.198. That is equal to 128.23 into 0.15. That is 0.079 into E3 plus 0.198 into R3. That is equal to 19.23, because 128.23 into 0.15 is 19.23. I am calling it as equation number 4. And then we got equation 5. Equation 5. Earlier equation 5 was obtained. It is R3 plus E3 is equal to 128.23. And then we got equation number 6, which is 0.079 E3 plus 0.198 RP. That is equal to 19.23. I am calling it as equation 6. Now we have to solve equation 5 and 6 simultaneously. From equation 5, E3 is equal to 128.23 minus R3. I will use it in equation number 6. So that will be 0.079 into 128 minus 0.3 minus R3 plus 0.198 R3, that is equal to 19.23. That is 10.13 minus 0.079 R3 plus 0.198 R3, that is equal to 19.23. That is minus 0.079 R3 plus 0.198 R3, that is equal to 19.23 minus 10.13. That is 0.119 R3, that is equal to 9.09. That is R3 is equal to 9.10 divided by 0.119. This is 9.10. So therefore R3 will be equal to 76.47 kg. Now E3 is a 128.23 minus R3. That is E3 is equal to 128.23 minus 76.47. That is E3 is equal to 51.76. So I get R3 as 76.47 kg and E3 as 51.76 kg. So that ends my calculations for stage number 3. So at the end of this calculation, I have got the value of X3. X3 is 0.198. Then I got value for Y3. It is 0.079. Then I got value for E3. It is 51.76 kg. And then I got value for R3, which is 76.47 kg. So with this, my calculations for stage number 3, they are completed. So now I will show all the quantities and compositions. We will also show the compositions that are obtained for the calculations. So for stage number 1, feed was 100 kg. The composition was 0.3. It was contacted with 40 kg of solvent. Ys was 0. So in the process, we got extract of 45 kg and composition in it was 0.115. Then we got raffinate. It was 95 kg and composition in it was 0.255. Then from stage number 2, again this raffinate phase was contacted with fresh solvent 40 kg. We got extract from it as 43.77 E2, and composition in it is 0.095. Then we got raffinate from it. The quantity is 88.23 and composition, that is X2, is 0.225. Then from the third stage, we got the raffinate from second stage is contacted with the fresh solvent. You get extract phase E3. The quantity is 51.76 kg and composition is 0.079. And then you get raffinate. The quantity is 76.47 and composition is 0.198. So in this way, calculations for those three stages, they are completed. Now we have got all the quantities, we have got all the compositions. So that ends our solution for part 1. Now we have to solve part 2. In part 2, we are supposed to carry out single stage operation. So feed is again 100 kg, weight fraction of solute in it is 0.3, and we are supposed to get raffinate whose composition is 0.198. The same composition that was obtained after stage number 3 in the previous case. So for this, we are supposed to find out the amount of solvent that is required, amount of pure solvent, here Ys is equal to 0, that is required. And then we will also find out the extract phase. Well, that is not our concern. We just have to find out the amount of salt. Okay, now let us do the calculations. For the single stage operation, the intersection of the tie line R3A3 with the line FS, that gives a point that will be used in this calculation. So intersection of the tie line R3A3. Why R3A3? Because we need to get the raffinate composition that is represented by point R3. So the concerned tie line is R3A3 and we are interested to find out its intersection with the line EFS, and that intersection point we will call it as point M, and we are going to use that in our calculation for the single stage operation. So tie line 3, which gives us the final raffinate composition, we are using that in our calculation. So this is point M, the intersection of tie line R3E3 with the line FS, that gives us M. I'm calling it as point M, and this point would be if you just look at the y coordinate of this point, it gives xm. So y coordinate of this point, it comes out to be 0.115. So in this case, xm is 0.115, and then we will use this in our calculation. So m is given as xm is equal to fxf plus s10 into ys divided by m. So xm is fxf plus s10 into ys, m is f plus s10. So let us do the calculations. We will use the given known values to get S10. That is the task. Okay, so we have got equation for xm. Xm is equal to fxf plus S10 into ys divided by f plus S10. Xm is 0.115, f is 100, ys is 0. So if you use these values, we will get 0.115 is equal to 100 into 0.3 plus S10 divided by 100 plus S10. That is 0.115 is equal to 30, because 100 into 0.3 is 30 plus 0, that is 30. So 0.115 is equal to 30 divided by 100 plus S10. That is 100 plus S10 is equal to 30 divided by 0.115. That is 100 plus S10 is equal to this will be 260.87. That is S10 comes out to be 260.87 minus 100. That is S10 comes out to be 160.87 kg. Thus, and the solvent that is required for the single stage operation, it comes out to be 160.87 kg. So with this, I end my discussion for this numerical. Here we have solved a numerical in two parts. In first part, we have found out various quantities, raffinate and extract phases for 3-stage cross current operation. And in the second part, we have solved we have got the amount of solvent that is required if the operation is carried out in a single stage in order to get the same final raffinate composition as was obtained with the 3-stage cross current operation. So with this, I end my discussion for this particular numerical. So thanks. With this, I end my discussion. Thanks for watching. Do subscribe to my channel. Tell your friends to subscribe to it. And if you really like my videos, please hit the like button. Do hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day. Thanks for watching and hope to see you soon in my next video. Thank you. Have a nice day.